This time, what if the path is a parabolic form or a curve? How do we parameterize our function in order for us to solve for the complex integral of the said function along the curve or parabolic path? Now, take note that if you're going to take the integral of your f of z on our path z, this time it's a curve. Of course, we're going to use the same process, f of z of t times the derivative of your z of t with respect to dt, or to t rather, along a and b. So we need to find the parametric form of z of t so that we can also get its first derivative, and in the process also identify the a and b values. Now, if the curve, okay, curve C is given by, let's say, it's a parabolic curve. We know that the curve is in the form of y is equal to kx squared, right? Because it's a parabolic form. And of course, in most of the curves, it forms a square or quadratic form, where k is a constant, then the complex form is, we know that originally our z is identified as x plus iy, but since y is equal to kx squared, take note of this, our y is equal to kx squared, z here, your y, you have x plus I times kx squared, okay, which would give us the value of x plus I k of x squared. If we let x, okay, if we let x be equal to your t, so that we can have here a function of t. So we will have here the form now of your z of t becomes t plus I k t squared. This is the parameterization of our parabolic or curve path. We are using here x is equal to t so that we can actually form for in terms of t, because earlier your y was introduced as kx squared. Now, similarly, your t is between a and b. How do we identify your a and b? It is said that for our a and b values, it depends on the starting point and the end point of your curve. So if, let's say, that our curve is actually from 0, 0 to 1, 1, so our a and b, or our a would start from 0 and would end at 1, because that's the direction of the curve, meaning the smallest value of that curve along the line or along the portion of that curve from 0, 0 to 1, 1 for a quadratic form is actually 0, and the largest point is 1. So you could have here a being 0 and b being 1. But it's not all the time 0 and 1. It depends on the starting point and the end point. If it's not given, we can actually represent it in other forms, but let us have it here for some illustration, clear examples, so we can actually look for the actual form of our z of t. Let's say c is the curve y is equal to x squared from 0 to 1. Okay, that would mean our form here, our what do you call this one, our z of t here identified with this, okay, our z of t is identified as your t plus I k t squared, but your k here is actually 1 as indicated by this value here. So you just simply remove that k, therefore you will have here I t squared. So t is again at 0 to 1 as indicated by this condition. That is already its z of t form. Its first derivative, which you also need for your integral here, is just to take the derivative of that with respect to t. The derivative of t is 1, and the derivative of it squared, where with respect to t is you have here 2i t, 2 minus 1. These are the two items that you need for your function here in order for you to verify the integral of or complex integral of a function. We will have, of course, examples later on to illustrate this further. Thank you very much for watching.